Hello everyone, welcome back to my video series on Introduction to the Finite Element Method in 1D. So at the end of the previous lecture, we started from the strong form and we used it to derive the weak form of the Poisson's equation in 1D. So the weak form can be expressed as, given some function f of x and some constants g and h, we want to find the solution u belonging to the solution space S such that the following equation holds true for all functions w belonging to the test function space. The equation itself can be written as integral over the domain 0 to 1 of dw by dx multiplied by du by dx is equal to integral over the domain of w multiplied by f dx plus w of 0 into h. The solution space S and the test function t are explicitly written above. So the set S is the set of all functions u such that u is an h1 function and u of 1 is equal to g, essentially the Dirichlet boundary condition. Whereas the test function space is the set of all functions w such that w is an h1 function and w of 1 is equal to 0. In this lecture, we are going to discretize the weak form in order to solve the Poisson's equation using the finite element method. But before we do so, we are going to introduce some notation in order to write the weak form in a much simpler way. So here's the new notation that we are going to introduce. Firstly, we are going to define a of w, u as the integral over the domain of dw by dx, du by dx, dx. So this is essentially our first term in the weak form. So a of w, u is equal to the integral over the domain of the derivative of the first term w multiplied by the derivative of the second function u. Similarly, we are going to define w, f as integral over the domain of w multiplied by f dx, which is our second term in the weak form. So w, f is integral over the domain of the product of the first term with the second term f. So with this notation, the weak form can simply be written as a of w, u is equal to w, f plus w of 0, h. So this is the purpose of introducing this notation to succinctly write the weak form. What's also particularly interesting is that for more complex problems in 2D, 3D, or more complex equations, we can also often reduce them in the form of the similar notation, and that's the purpose for introducing this notation. So before we go on, I would like to highlight some interesting properties of these two expressions, a of w, u and w, f. So here are two interesting properties of these expressions. The first property is that they exhibit symmetry, and the second property is that they exhibit bilinearity. Now what does that mean? So both these expressions are essentially symmetric, and what that means is that if you consider a of w, u, then that is exactly the same as a of u, w. Similarly, for the second expression, if you consider w, f, then that is exactly equal to interchanging them, f, w. Now why is that true? Let's have a look at the definition of a of w, u. So in this expression over here, if we interchange w and u, then since we're just multiplying them together, the integral won't change. And so obviously a of w, u is equal to a of u, w. Similarly, in the second expression, if we interchange w and f, since we multiply them, the integral doesn't change, and hence w, f is equal to f, w. So that's why the symmetry holds true. The second property that we highlighted was they are bilinear. So bilinearity means that they are essentially linear in both the slots, w as well as u in the first expression and w as well as f in the second expression. So what does that mean? So if we consider the expression c1 w1 plus c2 w2 for some constants c1 and c2, u, then this can simply be written as c1 times a of w1, u plus c2 times a of w2, comma u. Similarly, for the second expression, if we consider c1 w1 plus c2 w2 for some constants c1 c2 and some functions w1 w2, comma f, then this can be simplified as c1 times w1, comma f plus c2 times w2, comma f. And this linearity holds true for both slots. So if we replace u by c1 u1 plus c2 u2, then it can similarly be expressed. Now, why does this hold true? So if you look at the definition, since both the derivative as well as the integral are both linear operators, and hence instead of w, we have c1 w1 plus c2 w2, then the constant c1 can be pulled out of the derivative as well as the integral, and that's why this relation holds true for both these expressions. So now that we know about these properties, we can now move on to discretize the weak form using the Galerkin method or the finite element method. So we are going to use the Galerkin's approximation method for discretization. So in the original weak form, we are looking to find a solution u belonging to the solution space S and a test function w belonging to the test function space T. But the problem is that both these function spaces S as well as T are infinite dimensional function spaces. So in the discretization, we consider a finite dimensional subspace of both these function spaces. So instead of looking for a u belonging to the infinite dimensional space S, we look for an approximate solution UH belonging to a finite dimensional space SH, which is a subspace of the infinite dimensional space S. Similarly, we are going to look for an approximate test function WH, which belongs to the space TH, which is a subset of the infinite dimensional space T. So as I just mentioned, I'll highlight that SH and TH are finite dimensional subsets of the infinite dimensional spaces S, T. Now clearly, based on the definition of both S, T, we can say that immediately u of h at x equal to 1 has to be equal to g, that is the Dirichlet boundary condition, whereas w of h at x equal to 1 has to be equal to 0. So this is the first approximation that we make in the Galerkin method, that we are looking for an approximate solution UH which belongs to the finite dimensional subspace SH, which is a subset of the infinite dimensional solution space S. The next assumption that we make in the Galerkin method is that the approximate solution UH is expressed as a summation of two functions, a function VH and another function GH. Here, we assume that the function VH belongs to the test function subspace TH, and the function GH is basically some function which satisfies the Dirichlet boundary condition. That is, GH at x equal to 1 is equal to G. The reason for making this split is that since VH belongs to TH, we know that VH at x equal to 1 by definition has to be equal to 0. And by definition, we have enforced that GH at x equal to 1 is G, which means that UH at x equal to 1 has to be equal to 0 plus G, which is equal to G. So this definition of the approximate solution UH ensures that it also satisfies the Dirichlet boundary condition. I would like to highlight that the key idea of the Galerkin method is that in this split, the function VH belongs to the same function space TH as the test function WH. That's the key idea of the Galerkin method. This results in a simplified version of the set of equations that we'll derive later, and I'll talk about that when that comes. Now, let's consider TH, the test function space, to be consisting of all possible linear combinations of some basis functions NA, which are linearly independent functions. So let TH consist of, apologies, all possible linear combinations of some basis functions na, or a equal to 1 all the way up to n. So these functions na are called basis functions and are linearly independent functions. So what this means that any function wh which belongs to th can simply be written as a linear combination of these basis functions for a equal to 1 to n. Here the constants ca are just constants which are arbitrary. These functions na, as I just mentioned, are called basis functions, but they are also, in the context of FEM, sometimes called shape functions or interpolation functions. So at this stage, it is clear why they are called basis functions, because they form the basis of the function space th. But why they are called shape functions and interpolation functions, that will be clear a bit later. So from here, the other thing that we can see is that since we have n linearly independent basis functions, the dimension of the function space th is essentially equal to n. The other thing is that we already know that by definition, wh at x equal to 1 has to be equal to 0. And since wh is arbitrary, the CAs are also arbitrary. And so this relation essentially implies that the function na at x equal to 1 also has to be 0 for all values of a equal to 1 all the way equal to n. So this is another property of the basis function that we are already aware of. Now by the Galerkin method, UH can be expressed as a summation of VH and GH. And since VH belongs to the same test function space TH, it can also be expressed as a linear combination of these same basis functions. So we express VH as the summation of b equal to 1 to n db nb plus the function gh, which can be expressed as a constant g multiplied by another function n plus 1, where n plus 1 is used because we already have defined the first n basis functions. Now here n plus 1 is basically some function which satisfies an n plus 1 at x equal to 1 is equal to 1. So we already know that all of these functions nb at x equal to 1 are 0, whereas an n plus 1 at x equal to 1 is 1. So overall, this expression is going to satisfy UH at x equal to 1 is equal to G, the Dirichlet boundary condition. So here I would further highlight that the key idea of the Galerkin method is that the test function WH as well as the solution function UH essentially have the same basis functions NA. So that is the key idea of the Galerkin approximation. UH and WH have same basis functions. Now we will substitute these expressions for the test function WH and the solution function UH into the weak form to help us discretize the weak form. So the weak form can be written as A of the approximate test function WH, comma, the approximate solution function UH is equal to WH, comma, F plus WH evaluated at x equal to 0 multiplied by H. Now here WH is given by summation CA-NA, whereas UH is given by summation DB-NB plus G multiplied by NN plus 1. So we substitute these expressions into this equation, and that gives us A of summation CA-NA from A equal to 1 up till N, comma, summation DB-NB from b equal to 1 to n plus g multiplied by nn plus 1, that's the first term, is equal to wh, which is nothing but summation a equal to 1 to n Ca Na, comma f plus wh evaluated at x equal to 0, which is summation a equal to 1 to n Ca multiplied by Na evaluated at x equal to 0 multiplied by h. Now we take advantage of the fact that these expressions a and the second one over here are both bilinear. So they are linear in each slot, the first one as well as the second one. So essentially in this expression, the CAs can essentially be pulled out and the summation can also be pulled out for both summation CA as well as summation DB. The other thing that we observed is that the summation over CA appears in every term in this expression. So firstly, we just pull that out all together to be summation A equal to 1 to n Ca multiplied by the whole thing inside. For the first term, the summation over b can also be pulled out due to bilinearity. So it's summation b equal to 1 to n, and all we are left with is a of na, nb multiplied by the db's, which have now been pulled out. The second term over here can be written as a of na from the first half and comma. Again here the constant g can be pulled out, so we are left with n of n plus 1, and the constant g has been pulled out. Next, both these terms are brought back to the left hand side, so we have minus. Again summation Ca has been pulled out, so all we are left with is na, comma f, and the second term all we are left with is Na evaluated at x equal to 0 multiplied by h is equal to 0. So in this equation, dBs are the unknowns which we need to solve for. So knowing that, this equation can be further written in a succinct manner as summation A equal to 1 to n Ca multiplied by summation over B equal to 1 to n Kab times dB minus Fa is equal to 0. Here Kab is given by this first term over here, that's multiplied by dB, which is equal to A of Na, nb, whereas Fa is essentially everything that remains, which can be written as Na, f, this term over here, plus Na evaluated at x equal to 0 times h, which is this term over here, and lastly we have this term over here, which can be written as A of Na, nn plus 1 multiplied by g. So this equation over here, in this equation we know that since the test function wh is arbitrary, the constant Ca are also arbitrary, so this equation should hold true for all possible values of Ca. So for example, we can consider that C1 is 0 and all of the others, C1 is 1 and all of the other C's are 0, and that will give us the first equation for A equal to 1. Similarly, if we consider C2 to be equal to 1 and all the other C's are 0, then that will give us the second equation for A equal to 2, and so on. So essentially this equation reduces to a set of n equations which can be written as summation b equal to 1 to n Kab dB is equal to Fa for all A equal to 1 all the way up till n, or in matrix form this can be written as the matrix K multiplied by vector D is equal to F. So this right here is our matrix form M of the Poisson's equation solved using the finite element method. Here the matrix K is often in FEM terms called the stiffness matrix. The unknown vector D is called the displacement vector. And the right hand side F is called the force vector. So the reason for this terminology is that, let's say this represents an elastostatics problem. So in this case, the unknowns D are essentially the solution or the displacement of the grid nodes in the FEM method. F is actually the force acting on the body, and K represents the stiffness of the body. And so that's why we have this particular terminology. The other thing that I would like to highlight is that once we assemble this matrix K based on the definition KAB and the right hand side F based on the definition for F, we can then solve this system of equations and get the unknown displacement vector D. And once D has been obtained, we can then generate the solution at any value x using this equation. So the approximate solution U of h, if you remember, can be written as summation b equal to 1 to n dB nb of x plus g multiplied by nn plus 1 of x. So by substituting the unknowns b's in this equation, we can then obtain the approximate solution uh at any value of x in the domain. So now we're pretty much done in terms of the finite element method. We took the weak form, we discretized it, and we expressed it in a matrix form. The only thing remaining to do is to actually assemble the matrix K and the force vector F, and once that's done, we can then solve the system of equations and generate the solution anywhere within the domain. The only thing remaining to figure out is how do we assemble the matrix K and the force vector F, and in particular, how do we define these basis functions or shape functions NB. We'll talk about that in the next lecture. Thank you for listening, and I hope you learned something.